This is Unit 12, Lesson 14, Part 2. So we are finally on to our last section of this very long unit. This we are still working within that trigonometric equations category, but finally for our last category, we've seen the simpler ones, we've seen the ones where we have to solve by factoring, and now we are moving on to using some of our identities. So just a little tip over here, some common identities that we might see are the Pythagorean identities, the reciprocal identities, or even the double angle formulas or identities. So just to remind you of what those are, I have copies of some of our old notes here. So the Pythagorean identities are these ones. Almost every time it's going to be some combination of this one. So it might be this, or it might be the one where we subtracted part of it from one side or the other. So like cosine squared equals 1 minus sine squared, or sine squared equals 1 minus cosine squared. That's typically what you'll see is some combination of that. We have the reciprocal identities. You might also see one of these, the quotient identities, or we have, from a little bit more recent, some of these double angle identities. And those will be pretty obvious when you're supposed to use those because you'll see either sine of 2 theta, cosine of 2 theta, or tangent of 2 theta right there in your equation. So you'll immediately know to replace with one of those. All right, we still want to have our unit circle at the ready because when we isolate our trig expression, we are then going to be looking on our unit circle to find angles that match. Okay, so notice here, we are looking anywhere between 0 and 180, so just the top half of the unit circle, and we want to give all of our solutions in degrees. So we're going to do 4 of these examples, starting with number 15. All right, so here I mentioned the double angles. As soon as you see this, that is where you just know that you are going to work with our cosine of 2 theta. All right, you're going to do the double angle. So let's take a look. We've got this right here. So we have cosine of 2 theta. Now we've got a couple of options here. I mentioned during this section that 9 times out of 10, it's going to be this formula that we use. So if we look at this, we do have a couple of options and either one makes complete sense. We could do the top one or the bottom one. This one, if we use this top one, watch what ends up happening. If I plug this in here, I then add sine squared, and this negative sine squared will cancel. So this is actually one of the rare examples where it makes more sense to use this. Remember, you'd have a formula card in front of you, so you'd be able to kind of play around with which one makes the most sense. But we are going to use this to replace the cosine of 2 theta. So cosine squared minus sine squared. So that part that I underlined is going to be replaced with cosine squared minus sine squared. And then after that, so this was once the underlined part. And then we have plus sine squared, close parentheses, equals 3. We are doing 16, so try to save your space there. So now I have minus and plus the very same thing, so those will cancel. And then I have 4 times cosine squared on that left-hand side is equal to 3. So we want to isolate that trig expression. So for us, in this example, that means dividing both sides by 4. So I have 3 over 4. And then it's cosine squared, so I solve by taking a square root of both sides. So cosine ends up by itself. Do not forget your plus or minus when you're solving by taking a square root. Square root of 3 does not simplify, and the denominator of square root of 4 is 2. So we are looking for a cosine value on the unit circle that's either positive root 3 over 2 or negative root 3 over 2. So remember, that means you're doing a lap around the unit circle looking for x coordinates. And we're actually, just to remind you, not doing a full lap. We're just doing the top half, just till we get to 180. So here's our first one. That's a positive root 3 over 2. So look for the matching angle over here. There's that negative root 3 over 2. So in degrees, that would be 30 or 150. Okay, so that is our first example using a couple of those identities. The next one we're going to look at is the one right next to it, number 16. So you see that guy right there. You see the sine of 2 theta. That tells us to use our first double angle formula. Sine of 2 theta is 2 times sine times cosine. So replace that. Okay, so then we solve using the same techniques that we did in part 1. So this is actually going to be a solving by factoring. Okay, it looks kind of complicated. Notice between these two, we have a GCF that we can factor out. This expression and this expression both have a factor of cosine that I will factor out right now. So without the cosine, factor out that cosine, and this one is just 2 times sine. Minus, and then with this one, factor out the cosine. Don't forget that there is still a 1 left behind. So now I technically have 2 different pieces here. I can set each one of those factors equal to 0. Okay, so this is just set. Let's solve this one, get the trig function isolated. For this one, I would add 1 to the right and divide by 2. So 2 different things that I'm going to look at on my unit circle. I am looking only on the top half, just between 0 and 180. So when cosine is equal to 0, that's the x coordinate. That's this point right here, so 90 degrees. And then sine is equal to 1/2. All right, so remember sine is the y coordinate. There's a y coordinate of 1/2. There's a y coordinate of 1/2. So 30 degrees, 150 degrees. Remember, we only want the ones from the top half of the unit circle. Okay, 2 more of these. Let's do the one underneath, number 18. So now this one, we see cosine squared, cosine, sine squared. The left-hand side seemed pretty promising that we were just going to factor this stuff down. Remember, these are like x's, and this is like a y. So for this one, you really can't solve anything if you have this combination of x's and y's. So we are going to replace this, and we're going to do it with that Pythagorean identity. So remember this one. If I take just this, and I want to get it by itself, that sine squared, to isolate it, I do 1 minus cosine squared. Right, like I take this piece right here and I subtract it over to the right so that sine squared is by itself. So if I have sine squared, I can replace it with this, which is what I'm going to do. So my right-hand side is 1 minus cosine squared. Left-hand side doesn't change. This is now a factoring example. So because it's a factoring example, I want to get everything on one side of the equation. So let's pull these pieces over to the left. So add a cosine squared. I now have 2 cosine squared. No cosines over here, so I just have this minus cosine. And then I have a 1 over here, 1 over here. When I subtract them, they actually cancel. So that's what my equation is so far. So this is not going to be traditional factoring. It's actually going to be another GCF like I did with number 16. So these two, think of this as like 2x squared. Think of this as an x. They have an x in common, which means this one has a cosine in common. So I factor it out, leave the leftovers in parentheses. This leaves a 2 and an extra copy of cosine. This, just like number 16, don't forget it leaves a -1. Okay, so this one's actually going to be really similar to number 16 in the factoring sense. This is just going to be cosine instead of sine. So when I set cosine of theta equal to 0, just like number 16, I know I get 90 degrees. And then when I set this equal to 0, just like 16, you add 1 and divide by 2. So this time, you're going to get different angles because sine goes with y, but cosine goes with x. So I want the ones on the unit circle that have an x coordinate of 1/2 this time. So that would be this one, 60. And then it's only positive 1/2. So this one doesn't count because it's negative. And this one, where'd it go? This one doesn't count because it's 300, and I only wanted to go between 0 and 180. So for this one, I actually only use the 60 degrees. If it's going to bother you that these are out of order, feel free to write them in numerical order. I'm just putting them in the order that I found them in the problem. So I really do not care if they are in order or not. All right, last one, number 20. You see a quadratic. So just like this one, it seems like we should be factoring, and we will be, but we can't have this mix of sine and cosine. So this is sine, this is sine, this is cosine, and it's one of our double angle formulas. So we're going to replace it. And remember, with the double angle formulas, we have options. So we have 3 different options. This stuff was already for the majority in terms of sine. So you want to stick with this most common one because that'll be all in terms of sine. So we're going to replace cosine of 2 theta with 1 minus 2 times sine squared. Okay, so that's my underlined part. And then just keep on writing the rest of it. Okay, lots to write there. There we go. That's a 0 in the end. So combine up my like terms. These two combine up to 6 times sine squared. This is my only sine, so I have 11 sine theta. And then I have a 1 plus 3, which would be a 4. Okay, this is a 6, obviously. The 6 does not divide out of any of these pieces. So if my leading term here does not divide out, you do the slide and divide for your factoring method. So take this 6, slide it to the end, and multiply by the 4. That does not change your middle term. The 4 gets multiplied by the 6. So still factoring, I have a sine squared here, which means I start with sine times sine, kind of like y times y. And then I'm supposed to be multiplying to 24 and adding to 11, and that would be 8 and 3. They multiply to 24, they add to 11. Finish off the slide and divide. A lot of people forget to finish it, and they just like leave their answer like this, but I need to divide out that 6. Okay, so 8 over 6 reduces to 4 over 3. 4 over 3 means the 3 slides back to the front. 3 over 6 reduces down to 1 over 2. 1 over 2 means the 2 slides back to the front. Okay, so now solve these. Set them equal to 0 and solve. So this one, to get sine by itself, I would subtract 4 and then divide by 3. For this one, I would subtract 1 and then divide by 2. This, negative 4/3, that is too small. The lowest I go is negative 1, and this is outside of that scope. So that's not going to give us anything. This one, negative 1/2. Let's check our unit circle one final time. Negative 1/2 for sine would be the y coordinate. That's 210, and I have another one at 330. However, these problems said 0 to 180 only, so this doesn't work out either. We do come up with angles, but just not angles that come up inside the range. Like, just to show you, we did come up with answers. We had 210 degrees and 330 degrees. However, they're extraneous because they're outside of the set domain that was given to us. So for this one, we actually just say that there is no solution. We had a bunch of answers that didn't work out for different reasons. This didn't fit in our set range for sine. Sine only goes from negative 1 to positive 1. This did not fit inside our domain because our domain of theta values only included 0 to 180.